Thank you. I will talk about the validation of ray tracing algorithm we have implemented in our PV simulation software. It's work of my colleagues, and I have only the pleasure to present the results. Our company Solargis is known probably to you more as one of the data providers, but our scope of the work is much wider. We are providing our data to customers in more than 100 countries, but we don't only provide the data, but on the top of this data, we develop various services, and we provide platform for site selection and preliminary evaluation. Then we provide high quality data and additional services like site adaptation, quality control of the data. And then we provide also services for monitoring and forecasting of PV power plants. So it is not only data, but also simulation tools on the top of this data analytics, and to support the solar industry. For some of our products, we already for more than 10 years are providing also PV simulation. This original PV simulation tool is based on simple surface model by Tomas, but we saw a few years ago that with emerging new technologies, this simulation tool is not sufficient, and we decided to develop a more complex simulation tool, and it is based on ray tracing and view factor methods. If you can select which one, or depending on the detail we want to do the simulation, it allows very detailed scene creation with shading objects and like inverter boxes. In electrical part, it is based on single diode model, detailed inverter transforming cabling losses models. It allows simulation to 1 minute data, up to 1 minute data, multi-year time series. Currently, status of the development of this simulation tool is that we are using it already for our consultancy services for specific simulation of more complex power plants. But in this talk, I would like to give some results of validation of optical part of this simulator, which is based on comparison with bifacial radiance, detailed ray tracing model, and we also compare our results of this optical part with the ground measured data. We did also, of course, the electrical part, and using LT-SPICE. Definitely, we did also comparison with other available softwares for PV simulation. Currently, we are working on improvement of computational performance, because in general, ray tracing methods are very demanding for calculation power. But there is still a big space for improvement and to really decrease the processing time of this calculation. Now we are also implementing some more complex snow and soiling losses models into this PV simulator. The PV simulation is split into 13 individual calculation steps. This blue part is the optical part, where we are, the core is this ray tracing and transposition model using this ray tracing. But there are like angular reflection, soiling, and so and other sub models. In electrical parts, it ends with consumption, transformer losses, inverter losses. A model requires a lot of detailed technical inputs, environmental, meteorological, like basic radiation data, temperature data, albedo, snow information. The core of the optical part of this system is ray tracing algorithm. The custom implementation of this method, it is used for calculation of the irradiance on the arbitrary surface. We do calculations at the level of individual cells of the PV models. For this ray tracing, we decided to use and implement Monte Carlo backward path tracing model. So it is based on the principle that we are casting from the PV cell rays in various directions, and we are looking after several bounces when it reaches the source of the light. This method, as it supports multiple bounces, and there is no limitation, it just prolongs the computational time, allows to really do simulation of universal 3D scenes, so very complex. And our goal was, of course, to support PV simulations for bifacial systems. This ray tracing model is a part of the simulation, and it has to be based or coupled with a sky model. And in our simulator, we implemented Perez models, both isotropic and anisotropic, or all weather sky model. But we can, if there will be another model for sky, it can be easily replaced. The design of the ray tracing was done done in a way that we can use whatever model for sky, but I will focus in my validation for these two models. What is the difference? Isotropic model, it is probably well known for many of you. The sky dome is split into three areas. One is circumsolar, one is horizontal belt, and one is and the rest is so-called isotropic background or isotropic sky. And it is very simple, but I would say still quite powerful and easy to implement model. But for better or more realistic description of the sky, we implemented an anisotropic model where, unlike here, we have really uniform horizontal belt, circumsolar, and sky dome part. Here, everything is continuous, and it represents much better the sky conditions. Just to give you an idea, what does it mean to do ray tracing calculations? On the example of 4 megawatt peak power plant, 1 year of time series data, backtracking, with backtracking, I think it was a single axis tracker, bifacial. At the PV cell level, the calculation using GPU hardware takes 10 to 15 minutes for hourly data, 15 minutes takes up to 1 hour. And if there is linear increase with increasing the time step or into final results. Okay, this was like the description of ray tracing, which we are using, and now I move to the first part of validation. It is verification comparing the measurements from BMS station. We selected year 2021 from the big amount of data available at this station because the tracker systems were available since 2020 years. So we decided to go for 1 year validation. Uh, uh, Along with these trackers, single axis and two axis tracker, we were looking also to south facing fixed mounting and vertical mountings. There are different instruments available for various mounting uh, strategies, but I will come back during the interpretation of results. Important step was again quality control of the data. There were plenty of tracker malfunctions and other suspicious data which were excluded from the validation. The principle of the validation was that we took measured DNI, measured GHI values together with local measurements of albedo. We ran the simulation and calculated GTI or plane of the array radiation, and we compared it directly with measurements for even mounting type. We did comparison of both anisotropic and isotropic models, and we were looking to bias and RMSD. So what are the results? So it was quite surprising for us because we can see here mounting types with very good performance of this model, but we see also if you look to the bias, some of the mounting strategies which have quite big deviation. If you look to this first group, we see like for example for fixed system with 30 degrees tilt, that the performance of both isotropic and anisotropic models are almost identical. Bias below 0.01%, low RMSE. So for such configurations, both systems perform very well, or both sky types. If we were also interested that if we do aggregation of the data to 15-minute or lower resolution, whether still the model performs well or whether there is some degradation of the performance, because our simulator allows simulation for various time steps, but we see that the performance is very similar. Bias is slightly lower, but this is probably a result of some smoothing, and also RMSE. In previous slide, it was 5%, and for 15-minute data, where you have lower noise is as expected, slightly lower, below 4%. The similar results we achieved also for single axis tracker, very low bias, and RMS is very similar to the fixed system. And for two axis tracker system, the RMS is slightly higher. We see here also some outliers, so probably data cleaning was not done perfectly, but still performance of both isotropic and anisotropic models looks like very consistent, only little difference. More surprising were results for these fixed vertical systems, which were in four directions. We see that south, east, and west provide very similar RMSE, and bias goes up to 10%, negative bias. We see in the scatter plots that, that there is like systematic underestimation of higher values, and this is like for all three systems. South facing vertical performs a little bit better than east and west facing. Probably there is more diffuse radiation for east and west. Therefore, there is also higher bias, but this is just one of the ideas of interpretation of this result. And last is north-facing vertical system, where we see that bias is like similar to the east and west, but we have much higher, significantly higher RMSD. Okay, in a north-facing system, it is there is almost no direct sun, only in the far part of the year for very low sun angles. So the situation of or result of simulations look like this. Again, bias for isotropic model is slightly higher, but the results are comparable. We were thinking that, okay, what is the reason behind this strange result? Because they are not very consistent. And our idea is that probably there are some model limitation. Maybe SGSIM model or ray tracing model doesn't perform very well. I will come back later to this ray tracing. Maybe description of the sky by these types of sky model is not enough realistic. But as I show on the first slide describing the instrumentation, we saw that for east, west, north, and south, there was lower accuracy instruments available. For north facing, there was PSP, but it is also known for lower accuracy for the measurements with low DNI component. So probably this is the main source of the problems we see in the results of the simulation, because the reference data we are using are of lower quality. Another consideration about the result was like representativeness of ground albedo. If you look to this side, albedo measurements are done in the area with low or sparse vegetation. But if we have measurements of north-facing system, the scene or albedo of ground is not like representing, for example, this concrete flat area or reflections from buildings. So probably this is again one source of the discrepancies for this extreme vertical system. And of course, I didn't mention that for this simulation, we didn't use local shading because we don't have detailed data about shading on this side. Second part of the validation is comparison to bifacial radiance, and this was very interesting to do this analysis, because if you it was on the one table of PV models simulation front side of the modules, and we see here big differences in diffuse component. And the issue our difference we see here is that in this simulation we used our bifacial radiance is based on this anisotropic model, and in this simulation we used this isotropic simple model, sky model. So while the comparison for the situation without near shading of the simulation were showing very good consistency of anisotropic and isotropic sky description. Yeah, when we go to the real cases of simulation in PV power plant, we see that isotropic model for nearby shading is not probably sufficient, and big differences were identified in the results of simulation. When we integrated this anisotropic model, then comparison of with bifacial radiance and our simulations were very consistent. Okay, they are still for both front-facing and back-facing situation. So it indicates that when we use the same sky model, the ray tracing of our model is very consistent with bifacial radiance. We have some more detailed pictures of simulation by ray tracing for the backside of the module. We see that during the day, the results are very consistent. In the low sun angle, there are some differences, but this is only few watts per square meter, the scale here. So it is very consistent. Definitely, our implementation of ray tracing is slightly different from bifacial radiance. So we expect some differences, and but we see these results as very consistent. Okay, some summary of the results. As I said, we see for this optical part an implementation of this transposition model using ray tracing, very good match between bifacial radiance and other simulation. When I summarize the results of the simulations for this ground measurement data for sun-oriented surfaces like one-axis tracker, the two-axis tracker, and the fixed system, the feed was very good, but higher discrepancies were observed for these vertical systems where lower quality instruments were available only, and also description of 3D scene was very simple. We didn't include in our simulation because we don't have detailed description of the scene. So maybe this is the reason of the discrepancy. Okay, one question is that still is sky model this anisotropic sufficient for all the cases? As we saw these differences, it is difficult to decouple that what is a real source of these differences. So maybe also there is some space for improvement for new models which of sky description, which will better perform for bifacial simulation. Okay, we would like to also in the next steps to do validation of view factor comparisons of view factor ray tracing, but we started with ray tracing because it is like most detailed simulation we can do. So that's all.